New chapter, integrals. Oh, more specifically, this is multiple integrals because chapter 16, we're going to get thrown into these other weird integrals. And maybe Preston will talk about at the end of the semester. Anyways, we're going to deal with multiple integrals. We'll start off with some double integrals, and then we'll talk about the computation of these integrals symbolically with iterated integrals. And then we'll take it to different coordinates, polar coordinates, and then we'll go 3 integrals. Anyways, for today we're going to take a look at double integrals over these things, over a domain of a rectangular region. And before we do that, let's take a look at the area under the curve way back in, not way back, but whenever you took calculus. So let's do this recall business first. We, Calc 1 or 2, I guess they started to talk about integrals at the end of Calculus 1, and then Calc 2 they did more stuff with integrals. But in calculus, regardless, we have a function going from R to R. And I think this is where the ideas of where these things live, where the domain lives and where the range lives is going to be important. We have something in one dimension. And in one dimension, you're talking about a number line, essentially. And then your output here is also in one dimension. But when we take a look at the graph, we kind of put the graph in a two-dimensional setting where the x is the one-dimensional graph. This is your domain. And then you're given an interval that you're integrating over. So your graph, I don't know what your graph is going to look like. Your graph is going to look something like that, our generic idea of a graph. And then you essentially are looking for the area under the curve from A to B. And we know that that is, the area is going to be denoted by the integral from A to B of f of x dx. Now we want to backtrack a little bit to see where this comes from. And if you remember the Riemann sum, ideas of Riemann sum, that's pretty much where it comes from. And so what did we do? We took our interval AB and partitioned it. And those partitions don't have to be equal to each other, but for the sake of computational easiness, they usually think about them as being equal. And then we call them delta x and stuff like that. So this gets partitioned to some x sub 0, which is equal to a. I guess this is how they write it. A equals x sub 0, which is less than x sub 1, which is less than x sub 2, which is dot, 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 which is less than x sub n, the last one, which will be your b. And then we take a look at little subintervals, x sub 0 to x sub 1, x sub 1 to x sub 2, and then x sub n minus 1, the last one before, or the second to the last one and the last one. We take a look at these subintervals, and these all live in our domain from A to B. And then we pick a point. Now, generally, it's some random point. But then we got used to like picking the left endpoint or the right endpoint or the midpoint. Those are like the popular choices for these things. But we essentially pick a point in here that we usually denote it as x sub I star. And then by picking that point, we can put that point into the function to get the height of this rectangle. And then the base of this rectangle would be delta x. So we eventually come up with rectangles with a base of delta x and the height of the function evaluated at one of these x stars that belongs in one of these partitions. And so it's just base times height. We multiply these two things, and then we add up all these rectangles that we're putting together. And so we get the area to be approximately equal to the sum of x sub I, or x sub f of x sub I star times delta x. And then we take more and more partitions. We let n go to infinity, or the size of those partitions go to 0, whichever looks more appropriate from your, whatever you remember from your Calc 1 or Calc 2. And then that becomes the Riemann sum changing into the integral. Okay, so that's the general story, quick recap of things that I hope you are familiar with. If you know it like the back of your hand, and that's great. If you don't, this is like a quick summary, a quick reminder of what happened back then, because the same thing's going to happen here. Okay? So that's our recap. Now let's take a look at what's happening in our class. We're going to start off with a function and already we're in a little bit of a big change here, because our domain isn't just a single line interval. It's not just going from A to B, but our domain is in 2 dimensions. So already we're in a different world. We're in 2 dimensions. And so for simplicity's sake, let's consider a rectangular region in our 2-dimensional domain. And the thing is, we're going to need to be more flexible later on, hopefully later on today, where the region might not be a rectangular region. It could be something else. It could be a semicircle or a quarter of a circle. It could be some piece of a parabola. It could be something totally different, some exponential function. So we want to be flexible with that. But for starters, let's take a look at this and analyze this domain. So we need to spend a little bit more time in this domain. So let's take a look at this domain. Looking at this directly from the top, we can imagine that rectangular region is something that we can see flat. And we can even give it some values here, like say from A to B in the x. and then maybe from another two constants c to d in the y. And in the previous single variable example, we cut up the domain into little subintervals. Well, now our region is a two-dimensional plane, so the subintervals come in like two dimensions. So we can think about cutting the x up a little bit, and then we would also need to cut the y up a little bit also. I said also twice. Anyways, we have now a partition for our region, which is going to give us two-dimensional rectangles, squares if it's all nice and square. But we're not guaranteed squares here, so we're going to have these cuts. Now imagine these cuts over here. Right? Those are just little hash marks. So in this little partitioning that we did, we can call the little distances here to be delta x, and then the little distances along the y to be delta y. And we could take a look at an example of a square over here, or a rectangle over here, that would have a delta x and delta y value. Let's say that shaded rectangle is over here. Randomly selected. All right? So we can get formal with the partitioning, but I think you can look at the book to see, how they partitioned it and stuff. But it's the same idea. Now, what did we do after we partitioned it? Let's look back. We partitioned it, and we picked a particular value within each partition. And then we put that value into the function to give us our rectangle, and then we found the area. Well, as you can imagine here, we're probably looking for the volume under the surface. So we're looking at a three-dimensional object. A volume is what we're looking for. So you probably want to get a value in here, an xy. So let's call it xi star, comma, yi star. Let's call it j, sorry. Since the x and the y are kind of independent from each other, we can, maybe you might have 5 partitions in the x and 7 partitions in the y, so we have to keep those partitions separate. And so we're going to need 2 subscripts here in the I and in the j. So if we take that point that we got in 2 dimensions, and then we found the f of xy value of that, then that's going to essentially give us a height of some rectangular region. So we put that into the function, and then we're going to get some z value, f of xi star, comma, yj star. That gives you the height, and if I create a box out of that, I can find the volume of the box by doing the length times width times height business. And so I would have one sample of the box. That's a little too thin. You guys can just imagine this is actually straightened out, right? All right. So that's one region. So again, you have some sort of delta x, delta y, and then the height. And so the volume of this what word do I want to use? Volume of this piece is f of x I star y j star times delta x times delta y. Okay? So now we're going to run this delta x through and the delta y through all the possible y values and x values. Then we kind of have a Riemann sum embedded within a Riemann sum. So going along the x, we're going to add up all the x components, xi star, yj star, delta x, some I values go from 1 to some n. And then we're going to add up along the y. This time your index is j, going from 1 to not necessarily n, although they could have the same amount of partitions, but it could be m, slightly different. And now we have this. So that's how we're going to define our double integral. So we say double integral of f of xy over a rectangular, I'll put rectangular in parentheses, rectangular region R, and we'll do a shorthand notation for that. It's a double integral of f over R okay. So initially they use a dA for the combination of the delta x and delta y put together. And so this is going to be our notation for a double integral. And we'll need to remember, try to keep this notation in our heads, because when we do a triple integral, when we do line integrals, path integrals, surface integrals, flux integrals, all kinds of different integrals happening. And when we throw all that out, we're going to have to try to remember what a double integral is, because that's going to be our second easiest thing to remember. And our first easiest would be a single integral, which I'm hoping you guys all know how to integrate, right? All right. So, this notation here is just a general notation. We want a more working notation. And so in our first simple example where we're integrating over rectangular regions, we're going to integrate, I'll do this in kind of order on the inside first. We're going to integrate from a to b of f of xy dx, and then integrate from c to d of that result there, dy. And so this is how the definition comes to be. I, j, f of x, I star, y, j star, delta x, delta y. From I goes maybe 1 to n, j goes 1 to m. Okay, so this here is a definition. And this here would be kind of like the general notation. So I don't know if it's worth doing an example where we can actually integrate numerically or integrate symbolically and then find a numeric approximation, because that's the kind of stuff that can get a little tedious. But there are times or examples where you're kind of left with, you don't have the function. Maybe you do, maybe you don't, but let's say you don't have a function. All you have is a table, for example. And when you're dealing with a table, all you have are numbers, and you can't really come up with the integral, and so the best you can do is an estimate of something. So let's do an example where we're kind of forced to do that. And then you did some examples in your lab, I think, where you actually have to plug in some values into the function. So you can get practice doing that. Let's see. Oh, where am I? So here are a couple examples. Let's take a look at this one, maybe. We have a 20 by 30 foot swimming pool filled with water. Depth is measured in 5-foot intervals starting from one corner of the pool. Values are recorded to estimate the volume of the water in the pool. So this is an example where we don't have a function. All we have are numerical values. And let's identify some of these important values here. So I don't know if it matters, and I don't know if they have a particular system of determining which is x and which is y, but that's what we need to do. We need to figure out which is x and which is y. I don't know if it matters. I think in computers they have x going across and y going down instead of going up. So let's do it like that. This is your x value and this is your y value. So your x goes from 0 to 30, your y goes from 0 to 20. So that'll be your domain. So your region, if you want to think about this, you don't have to think about it like this, but if you do want to think about it and relate it to the graph that we saw earlier, your x goes from 0 to 30 and your y goes from 0 to 20. And so this is your, maybe I shouldn't shade that because we're going to cut it up. Into whatever, it has to be distances of 5, which is what they said. So this is our general idea of what's happening. So So we have values at 0, 0. We have values at 5, 0. We have values at 0 or 5, 5. And we have values at, what's the last one? 0, 5. Now you have values for a lot of them. But we have these point values here. So let's take a look at this, blow it up a little bit so we can just take a look at one rectangular region here. So, if you look at this, we can take a look at the z-values of those numbers. I'll put the z-values in maybe just right inside here. 0, 0 gets a z-value of 2. 0, 5 gets a z-value of 3. 5, 0 gets a z-value of 2. And 5, 5 gets a z-value of 3. So those are like the z-values. Imagine this thing going up. Those are going to be the heights. Or in this case, since it's a pool, those are the depths. All right. So what we want to do is we want to estimate this. Now we can choose one of these corners to be our representative point, because remember, for our point, we need an xi star and yj star to put into this table to give us a value, right? And since all we really have are 0, 5, 10, we can just use those numbers. So maybe for this first square, I might decide to use the lower left-hand corner to be my representative point. Just like back in Calc 1 or Calc 2, you would say, I would use the left endpoint. Or you can use the right endpoint. So in this case, we can use the lower left endpoint, the lower right endpoint. Now we have 4 of them, the upper right endpoint or the upper left endpoint. So we have 4 to choose from. Or what? Yeah. Oh, the x is here. So x is 5, 0, yep. So x is 5, y is 0, that's 3, and then when x is 0, y is equal to 5, that's 2. Yep. What were we talking about? What? Oh, picking one of these things. Yeah, so this first box, if we decide to pick the lower left-hand corner, we're going to pick 0, 0, and then that's going to give us a y value of 2. And then if we continue to go ahead and pick the lower left-hand corner for all the boxes that we're going to be looking at, we can just run along and figure out how far we're going to go. So we're going to, I should have talked about the partitions first. I mentioned the partitions, but I didn't identify them. What's the partitions going to be? What's the delta x going to be? these things are moving in increments of 5, right? So delta x, we could just see it over here, delta x is equal to 5. And likewise, if we take any two consecutive y values, the delta y's also equal to 5. So that gives us the base of this box, length and width of the rectangular region. In this case, it's a square, I guess. But that's going to give us the base of the box, and then the height, we'll just put it into the function, which will get these things. All right, so if we go along to x, we'll get, oh, you know what? The partitions in these boxes. Is it like that? They overlap. They overlap. That's going to make for a confusing picture. So, anyways, for this first box, I would, if I choose a left-hand endpoint, I'd be choosing this too. So, for the first box, let's see, I want to add up all these boxes. If I go along the x, these partitions over here, and I continually use the left-hand endpoint, I'm going to get my first box is going to be 2 times 5 times 5. By the way, the 5 times 5 is going to happen to all of them, right? So I can just take all that out. But I'll leave it there for now. That's my first box. My second box will be over here. And then the left-hand endpoint there, the lower left-hand endpoint would be this value over here, which has a z value of 3. And then if I go to the next one, maybe I'll use a slightly different color here. This is 0, 5, this is 10, 10 in the x and 0 in the y. So 10 in the x and 0 in the y, that gives me a y value of 4. You see what's happening? And so if I jump to my last box, I'm using my lower left-hand endpoint, I would be at this value over here, right? Which is not 30, but the one before that, 25. So I would add up these numbers up to here. So I would just go up to 8. And so this is the value that I'll be looking for. Okay? Yeah?
The table's upside down, right?
Yeah, I know. Yeah, on the table. Sorry that happened. All right, if we go to the next level up here, we're looking at this rectangle. And like Harrison said, it's upside down. So when you say lower left hand, it's actually the upper left hand for this. So it looks like you'll end up doing almost the same thing. Plus 2 times 5 and 5 plus 3 times 5 and 5. And then the last one, if I look at this last box over here, this would be the last box in the second level over here. The lower left-hand value is actually the upper left-hand value here, which is...
We know that the increment from these constants is 5 in the x direction, 5 in the y direction. So can't we just factor that out?
Yeah, we could totally factor that out. We should have factored that out just to make this a little bit easier. But I already have it written down, so I'm just going to keep it for now. And then anyways, we go to this box, to this box, to this box. And then, so in the y, we're going to take 1, 2, 3, 4 steps in the y. And so our last box in the y here, so I'm going to skip a line here that I'm not going to write out. But the last one is going to be essentially these numbers over here that I'm going to add up. So 2, 3, 4, 5, and then the last one's going to be 8. All right. So it looks like if you do what Evan said, and to factor out the 5 times 5 business, and then you essentially add up all these numbers that would have contributed so all these numbers in here that would have contributed to the lower left-hand corner of those boxes, then those are the values that we would have gotten. Okay, so you can just add all those up, and then that would give you an estimate. So that estimate, though, is just an estimate, and instead of using the lower left-hand corner, you could have chosen the upper right-hand corner and do the same activity, and you get a slightly different value. So if you do that for like opposite corners, that might be useful. You can find the opposite corners and then find the average between them or something. Okay? Yeah, is that good for now? Yeah. Gross over or underestimation. And so the better thing to do might be to find the midpoint. If you imagine these things having a height, if you imagine the possibilities of either having a height of 2 or a height of 3, you can just find the middle between 2 and 3 and just say, imagine this having a height of 2.5. And one way to do that, and didn't know if I wanted to get into this, is to take the average of all these numbers that are making up the heights of the square, and then that would give you kind of a better, more accurate approximation. It's not quite the midpoint rule, but it's close to it. All right. I wrote a program a few years ago. It's not really a program, but it's a Mathematica program that kind of takes a visual look at it. If we can imagine our, not imagine, but if we actually have a function that we can plug in values to, which is what's going to happen for us anyways. So let's assume that our function is this hyperbolic paraboloid that's been shifted up 4 units. And then our x values go from -2 to 2, and our y values go from -2 to 2. And then here it looks like I'll have 4 partitions. So in this particular case, I can use the lower left-hand point or the lower right-hand point, upper left-hand point, upper right-hand point. Or I can actually just find the middle, which is, I think, what this does. And then if we take those middle values and plug them into the function, we should get these. I'm looking at this from the top, and I have 2 dots because I have 1 dot that's on the floor and I have 1 dot that's actually on the surface. So they look like they're 2 dots. I got too many dots floating around there. Anyways, if I find those boxes, then I'll get some sort of rough approximation or a rough sketch of how this thing might look like. And what's cool with computer programs like this is that we can increase or decrease the number of partitions that we decide. And so if I increase this to like 16, then I get finer rectangles to look at. And that would be a better approximation of what's going on. Maybe I should get rid of some of the points. I think it's this one. So you can see the points below. I guess I have to look at it from underneath. Oh, they just look like, yeah, they look like points. And the partitions don't all have to be the same. I can make one partition be like 16 different rectangles, and I can make the other one to be 8. And so when I look at it, it's not perfect squares, it's rectangular regions instead. And we can still get an idea of if we find all these volumes of these rectangular boxes, then we can easily compute them. All right. So let's go. I think that's all there is to talk about for this section. We can get to the next section. So volume, double integral, numerical and graphical examples. What special case? So what we're going to do now is we're going to try to take a look at this and approach the double integral from a more symbolic perspective, algebraic perspective. And the way we're going to do that is we're going to take a look at sliced bread. So apparently the Cubs haven't won the World Series since sliced bread. Whenever sliced bread was invented. Who are you guys rooting for? Cubs. something about Cleveland that just kind of, maybe it was basketball, I don't know. So let's take a look at this area now. Instead of looking at the partitions, let's try to get a little fancier with the integrals that we know of. And what we can do is, kind of like when we took derivatives and we said partial derivatives, what we do is we fix a variable so that you pretend it's constant. And so let's do something like that. Let's fix a variable like it's constant. Let's fix this at y star, where it's constant. And y star would be some random point between some distance with delta y in it. So if we're looking at this double integral over our rectangular region, and for the moment we focused on where y is fixed. Now, I think I can keep this, wait. Okay. J goes from 1 to m delta y, and then I'll take this in a different color. Now, if I can go ahead and change this into an integral, this is my x value where y is fixed from where y is fixed at y star, and then this x value is just going to go from a to b. Now, the tricky part is that x is some fixed value, so I didn't do anything with the x. I have to assume that that's constant. Or, I'm sorry, the y. The y is some fixed value, so I have to assume that y is still constant. What I have eventually found, or essentially found, is a slice of the volume that I'm looking for. A slice of bread. Every time you eat a sandwich now, you're going to think double integrals? Yeah. Okay? So for a different slice, you're going to get a slightly different volume. But essentially, you're stacking up all these slices along the y. And so now, if we want to add them all up together, when we want to add them up, that's when the outer Riemann sum comes in. And so when the outer Riemann sum comes in, we're adding up the slices, so to speak. And when we add up the slices, where y value, your y value now goes from c to d, and so that becomes a definite integral from c to d of the thing inside, which is a which is just an integral, but now your variable with respect to y, which was once constant, once upon a time, is now going to be a variable in y. And so that is from a to b of f of x, y, dx, and then dy. Yeah?
Did you say that the original, the inside integral is just the area of the slice, and then we're basically adding up an infinite number of slices for the second?
Yeah, so that's how the adding up the infinite number of slices, that's how the delta y becomes a dy in your integral. Yeah. The delta x becoming a dx would be one of these slices and adding up all these things along the x. So a Riemann sum again becomes an integral for the second time, and now what we have essentially is what they call an iterated integral, because just like the summation notation, we're actually going to integrate from the inside out. That's how we're going to do these integrals. We're going to integrate from the inside out. Okay? So let's do a quick example, the example that we were just looking at. Example, let's take a look at the function f of xy is equal to x squared minus y squared plus 4, where r is going to be the rectangle from minus 2 to 2 by minus 2 to 2. And when you read something like this, you should imagine that this is your x limits and your y limits, and it's going to be a rectangular region. Or in this case, since it all has equal sides of 4, then we know it's a square. So we're going to set up our integral. Our inner integral is, well, the function is going to be x squared minus y squared plus 4. We're going to integrate with respect to x, and our x limits go from minus 2 to 2. And then we're going to integrate with respect to y, where our y limits also go from minus 2 to 2. Should we change one of these to 0, just so it looks a little bit different? Which one, the x or the y? Doesn't matter. I'd rather deal with 0 if I had a choice. Let's make the x go from 0 to 2. So the x goes from 0 to 2. So how would you do this? Well, basically how we laid it out when we were talking about this, we're going to do an iterated integral from the inside out. And we're going to integrate the inside with respect to x first, which means we're going to treat y like it was constant. Imagine y is like 5 or something, and then see what happens. So this integral here is going to be, with respect to x, 1/3 x cubed minus, now this is a constant. What's the integral of 5? 5x, right? So we have to keep the y squared as a constant, and then we throw in another x. And then for x, the same thing over here. Now, this is an integral that we're integrating with respect to x from 0 to 2. And just for good measure, I usually like to label this as x equals 0 in case I get confused with my variables later on. Now, remember that this is still the inside of the integral, and I could do this off to the side or just keep carrying it down here. But we need to plug 2 in, and we need to plug 0 in. Fortunately, when you plug 0 in, it gets 0. So this is 8/3. And remember that y squared is still a variable, so I'm looking at this. I need to put 0 and 2 in for x, not y. So this is still y squared, and then I put 2 in, and then 4 times 2. And then this whole stuff, when you put 0 in, you just get 0. I suppose it might be worth simplifying this because we're going to integrate it again. So let's simplify this. You got 8 plus 8/3 is 32/3. So that is what we have in our inner integral. And notice in our inner integral we have a function that has a y in it. But that's okay because our next step we're going to integrate with respect to y. So this is just another integral, and this is our last integral, our second integral. Now we just integrate with respect to y. This is 32/3 y minus 2/3 y cubed, and this goes from -2 to 2. We put 2 in there. 32/3 times 2 minus 2/3 times 2 to the third. And then we put in a -2. So it looks like if I put a negative, since this is an odd function, if I put negative values in there, it'll just make everything negative, which means if I subtract a minus, then it's just like multiplying it by 2 or whatever. However you want to think about it. 64/3, 8 times 2, 16/3. And I'll get the same thing, so I'll just multiply it by 2. $48, 96/3, and that's divisible. 32. Whoa. 32. Okay. That's the last integral I'm going to do in this class. All right, so for Beanies Theorem, in a way, I kind of don't want to talk about Beanies Theorem, but you know they talk about it in the book, so let me just tell you about Beanies Theorem. Beanies Theorem says that if you're integrating over a rectangular region, then you can actually switch the order of integration, which is fine. I guess that's a good theorem. Shouldn't matter. But this only will work for rectangular regions. So the whole idea behind Beanies Theorem is that you stack it up one way, you slice the bread one way, and you slice the bread the other way, you're going to get the same volume. But slicing the bread over a rectangular region looks like this. Just being able to switch the order and switch the limits and stuff like that, that's not an issue. So if you look at the iterated integral, you can integrate with respect to y first or integrate with respect to x first. As long as you're keeping the limits with the x and the limits with the y, that's going to be okay. But when we start dealing with more complicated regions, which is what we're going to do next time, we're not going to be able to just switch the order. I mean, we can switch the order, maybe, but switching it is not as easy as switching it like this. So we have to be really careful about that. Okay? So there's one more important piece of information here that I'll put up now, but then we'll talk a little bit more about next time. And that is the idea that if your function can be seen as factors, I have these weird red and blue underlines because I didn't change my settings. But this is not Beanies Theorem. This is just another property that if your function can be separated as two different factors, one factor with all x's and one factor with all y's, then you can actually split up your integral into two pieces like this. This is going to come in really handy, and next time I'll do a quick example of how this works, but it'll come in really handy when we start doing double integrals in polar coordinates and maybe even triple integrals.
I think I see how it goes.
Yeah, well, we're out of time, so I was squeezing this. Something about constants coming out. All right, next time.
Shouldn't